Bismillahirrahmanirrahim. Assalamu alaikum. Today my topic name is nitrene as a reactive intermediate. Firstly, we discuss table of content. Here table of content. Introduction of nitrene, electrophilic, electronic state of nitrene, stability of nitrene, classification of nitrene, generation of nitrene, reaction of nitrene, application of nitrene, future trends and developments in nitrene. Conclusion. Introduction. Nitrene is a highly reactive intermediate in chemistry that contains a nitrogen atom with two unpaired electrons. It is denoted by the formula Rn, where R represents an organic group or a substituent. Nitrenes are formed through various methods such as the decomposition of azides or oxidation of amines. Nitrenes are reactive intermediates that play a significant role in organic chemistry by enabling the synthesis of nitrogen-containing compounds and contributing to the development of new synthetic methods. Electronic state of nitrene. The main difference between the triplet and singlet electronic state of nitrene lies in the orientation of spins of two unpaired electrons. Triplet electronic state. In the triplet state, the spins of two unpaired electrons in the nitrene are parallel, resulting in a net spin of 1/2. This configuration follows the Hund's rule, which states that electrons occupy separate orbitals with parallel spins before pairing up. The triplet state is generally more stable and commonly observed for nitrenes. Triplet nitrenes exhibit radical-like reactivity and participate in reactions such as addition, insertion, and cycloaddition reaction. The second, singlet electronic state. In the singlet state, the spins of two unpaired electrons in nitrene are antiparallel, resulting in a net spin of 0. This configuration involves the pairing of unpaired electrons. The singlet state is less commonly observed and typically less stable than the triplet state. Singlet nitrene can exhibit distinct reactivity compared to the triplet nitrene, often involving concerted process and different reaction mechanisms. Electronic state of nitrenes can be influenced by several factors, including the nature of substituents, reaction condition, and the presence of specific catalysts or reagents. The determination and control of the electronic state of nitrene are important considerations in understanding their reactivity and designing the synthetic methodologies involving nitrene intermediate. Singlet state sp orbital, p orbital occupied, p orbital vacant. In the second triplet state, sp orbitals have lone pairs and p orbitals half-filled. Nitrenes are a very reactive species and cannot be isolated. However, a nitrene has been trapped by its reactive with carbon monoxide to yield an isocyanate. Nitrenes can also be trapped in the presence of ethylene. Classification of nitrenes. Electrophilic nitrenes. Electrophilic nitrenes are electron deficient species that behave as electrophile. They are attracted to and react with nucleophile species such as a carbon-hydrogen bonds to form a new bonds. Electrophilic nitrenes commonly participate in the insertion reaction where they insert themselves into CH bond, leading to the formation of new carbon-nitrogen bonds. These reactions are often regioselective, with the nitrene selectivity is selectively targeting specific CH bonds based on factors such as the steric hindrance and electronic effects. Electrophilic nitrenes are valuable in CH functionalization reactions and the synthesis of nitrogen-containing compounds. Nucleophilic nitrenes. Nucleophilic nitrenes are electron-rich species that act as a nucleophile. They attack and react with electrophilic center or species, resulting in the formation of new bonds. Nucleophilic nitrenes typically undergoes the addition reactions where they add to unsaturated bonds such as a carbon-carbon double or triple bond to form new carbon-nitrogen bonds. These reactions can lead to the formation of aziridines or other cyclic nitrogen-containing compounds. Nucleophilic nitrines are involved in various transformations and can participate in Cassie-Kite reaction to generate a complex molecular structure. Generation of nitrene. Some method. Firstly, we discuss the decomposition of azides. Thermophotolytical decomposition of azide can give the nitrenes. These are three methods by the decomposition of azide, or we get the generation of nitrene. Oxidation of primary amino groups in an amino compounds. Removal of two hydrogen atoms from an NH2 group can potentially form a nitrene. Deoxygenation of nitro compounds. By the deoxygenation we get also the nitrene. Formation of aziridines. Usually, nitrene generated from the azides react with olefin to form the aziridines. Again, azides themselves combine with olefin to form a triazolines, which may again be decomposed photochemically to form the aziridines. In the first we photolytic condition apply, in the second we apply the heat condition and get the triazoline derivative, and by applying the photolytic condition aziridine derivative we get. Formation of aziridines like carbene singlet nitrines react the stereospecifically, and triplet nitrines react stereoselectively through the diradical formation. In this reaction, two type of electronic state of nitrene: singlet nitrine and triplet nitrine. Different product we get. First product by the singlet nitrine, stereospecific product. In the triplet nitrine we get the stereoselective products. Formation of aziridines. It is to be noted that when the azide is subjected to photolysis or thermolysis, singlet nitrine is formed, and when the concentration of the olefin is large, the reaction is mostly stereospecific, but if the reaction medium is diluted with an inert solvent, the singlet nitrine is converted into more stable triplet state by clean with inert solvent molecule, and the reaction switches over to the stereoselective nitrine precursor azide. Two conditions apply: photolytic and thermal. In the singlet nitrine olefin use a stereospecific reaction, inert solvent, and triplet nitrine olefin stereoselective reaction. Formation of aziridines. Aromatic hydrocarbons react with nitrine to give the aziridine first, which undergoes the ring expansion to give the azipines. Insertion reaction. Like carbenes, nitrines also undergo insertion reaction. Singlet nitrines insert in a concerted manner, and the stereochemistry if the substrate should be retained in the product. Triplet nitrine could give the same, but by the two-step processes, two radicals are formed which combine to give the product. Insertion reaction. Nitrine intermediate are found to be involved in many intramolecular insertion reaction of the tertiary CH bond is at the asymmetric carbon atom. Then the configuration at the chiral center should be retained in the concerted manner. Metal catalyzed CH reaction. In this method, metal catalyzed CH reaction ring expansion process occur. Beckmann rearrangement. In the Beckmann rearrangement, oxime converted into give the product and substituted amide. These two types of rearrangement, Hoffman and Curtius rearrangement. Hoffman and Curtius rearrangements of amides and acyl azide respectively that put CO2 through an isocyanate intermediate. In this mechanism, both intermediate are formed, isocyanate intermediate and the product we gain amine. In the Huffman rearrangement, both rearrangement proceed through the similar key rearrangement steps. In both rearrangement, break the CCA bond, form the CN bond and break an X bond. Nitrines are reactive intermediates that have the variety of application in organic chemistry. Some of the most common applications of nitrine include amination of alkenes and alkynes. Nitrines can be used to add an amino group to alkenes and alkynes. A reaction known as aziridination. This reaction is often used to synthesize hydrocyclic compound CH amination. Nitrines can also be used to aminate CH bonds and a reaction that is known as a CH insertion. This reaction is often used to synthesize amino acids and other biologically important compounds. Nitrene-mediated cyclization reaction. Nitrines can be used to catalyze the cyclization reaction, which are reactions that form the rings from open chain molecules. This reaction is often used to synthesize natural products and other complex molecules. Nitrene-mediated polymerization reaction. Nitrines can be used to polymerize monomers and a reaction that is known as a nitrene polymerization. This reaction is often used to synthesize polymer with specific properties. The another application of nitrene is the reaction scheme for the synthesis of phenylalanine from the benzyl azodicarboxylate and styrene. The first step is decomposition of benzyl azodicarboxylate to produce a nitrene. The nitrene then adds to the alkene styrene to form the aziridine's product. The aziridine product can be hydrolyzed to form the phenylalanine. Synthetic application, Sandermeyer reactions. It is used to synthesize aryl halide from anyl disonium salt using copper salt as a reagent or catalyst. Cambridge reaction. It is an aryl-aryl coupling reaction via disonium salt. And we get the product biphenyl. Feature, trends and developments. Catalyst development, designing the efficient catalysts for the nitrene generation and controlling reactivity to enhance the synthetic utility. Selective nitrene transfer, development method for controlling the nitrene transfer to specific functional groups or position within a molecule, expanding the scope of nitrene-based transformations. Asymmetric nitrene chemistry, developing chiral catalyst and strategies for high enantiomer selectivity in nitrene-based reaction for the synthesis of enantiomer pure nitrogen-containing compounds. New nitrene generation strategies, exploring alternative reagents and methods such as photolytic and electrochemical approaches for nitrene generation, expanding the synthetic toolbox. Conclusion. In conclusion, nitrines serve as important reactive intermediates in organic chemistry. They are formed through the various methods including thermal decomposition of azides, photochemical reactions and oxidation of amines. Nitrines exhibit a triplet electronic state and possess two unpaired electrons, making them highly reactive species. Their reactivity include addition, insertion and cycloaddition reaction, allowing for introduction of nitrogen-containing functional group into the organic compounds, and nitrene finds application in organic synthesis, particularly in CH functionalization, aziridination reactions and nitrene transfer process. Mechanistic study and stereospecific characterization techniques contribute to understanding their behavior. However, the challenges persist in the generation and controlling the nitrene with high selectivity and safety consideration. Overall, the versatility and significance of nitrene chemistry as a reactive intermediate pave the way for future development in synthetic methodologies and design of nitrogen containing compounds. Thank you for listening.